Hi everyone, we're the Engineering Chicks. I'm Ashley and I'm here with Emily, and today we're going to be talking about the manifestation of uniform random numbers. So this is all about linear congruential generators, and what that does is it generates a series of pseudo-random numbers based on the recurrence relation formula that we have here. And a pseudo-random numbers are numbers that aren't exactly random, but they pass randomness checks. So you can use them like random numbers. So here, I'm just going to talk real quick about what each of these parts of this formula are. So M is the modulus here, and this also ends up being the period. And we'll talk about that in a second. A is the multiplier, C is the increment or the remainder, and x sub 0 is the seed. And this is where these become hard to predict. Like if you don't know the seed, you're not going to be able to predict what the next number in the series is, and that's why they're considered pseudo-random. So at some point the numbers will begin to repeat. So in practice you want the numbers to repeat after as long a time period as possible. So we're going to talk about two different kinds of generators. This first one is called a mixed generator. So in this case, C is greater than 0. And to create a full period, the point at which numbers begin to repeat, it's just best practice to make C an odd number. And then a good choice for M is this rule here, M equals 2 to the B, where B is the maximum number of bits used to represent integers on a computer. So B is normally 32. So if you follow these general rules, you should be able to generate a series of numbers with a full period, so that you have your numbers repeating after the longest time period possible. So the second type of generator is a multiplicative generator. So in this case, C is 0. And you never want x sub I to be 0 because all the following numbers will be 0. And in this case, the period can't exceed m minus 1. So a full period can only be reached if m is prime and if a is a primitive root of m.
Alright, so now going into section 2.2, the theoretical test for random numbers. Just starting out, most linear congruential generators are one of the following three types, which this is a snippet from the book, where lambda is the period. So you have type A, which is a full period multiplicative, and you can see the conditions for the parameters right there. And then you have type B, which is a maximum period multiplicative. And then you've got type C, which is a maximum period multiplicative, but as you can see, the lambda values differ, and the A and M are different. So you've got different parameters for each of those. And then the output from type C generators is identical to those of type A generators. The only difference is that in type A, you subtract the specified constant out. So, and then this has a theorem that goes along with it, and that's what's on this slide. So this theorem, it looks a little overwhelming, but it's not too bad. So you've got your M value, your A value specified, X naught should be an odd value, and then the proof, you just go through these steps that is displayed here. First you show that x sub 1 minus x sub 0 mod 4 is a multiple of 4, and then you assume that this is true for I equals k. And I won't read all of this just because it's a lot of like math terms and it's kind of difficult to go through verbally. But as you can see, this just proves that the results allow the investigation to be confined to the theoretical properties of type A and B generators only. And this theoretical test uses the values of A, C, and M to assess the quality of the output of the generator over the entire period. So if you want, you can pause and like read through this proof, but that's kind of what we just wanted to show out of that. Moving into some other points under the theoretical test for random numbers. So here's kind of where the idea of the lattice structure is introduced. And in this theory, it says that it would be possible to plot lambda overlapping pairs. So a necessary condition that for this to happen is that the sequence consists of independent, uniform distributed variables, and that all of the random variables are independent. And then the pairs should be uniformly distributed over the 0, 1 squared. So that's just the uniform distribution like squared. And if you check out these two plots over here, these are kind of two examples of it. And of course, it is unavoidable that all points can be covered by a set of parallel lines just because of the kind of theory that I just talked about. And then you can see that figure 2.2, this one down here, the one with more points, is preferred because the minimum number of lines it takes to cover all the points is much less than the one in figure 2.1. I think this one has 13, this one has 5, so the more the better. And then figure 2.2 is also more preferred because of the distance between the lines. So if you generally want a more narrow distance between the lines, and as you can see in figure 2.1, it's very wide. So now the next topic that I'm going to discuss is problems with increasing dimensions. And so when considering a maximum period multiplicative generator with modulus n equals 2 to the power of b in a period n minus 1, the distance between neighboring values is constant and it equals 1 over n. And then, but when you go into generating points with, like we just talked about with the lattice structure, and the points are generated over the 0 to 1 squared uniform distribution, you take two consecutive random numbers from that. And so the average distance of a tuple to its nearest neighbor is 1 over the square root of n. So this kind of switches things around, and the random numbers go from being approximated by a continuous distribution to being approximated by a discrete distribution. And so when this happens, the graininess of the discrete approximation to the continuous uniform distribution might become an issue. So basically, to avoid this issue, you want to increase the period. And this can be done in a number of ways, but 3 of the main ways is shuffling the output in order that the number of possible k tuples is much greater than n minus 1. And then you can also use a Toddsworth generator, or you can combine generators. So that's kind of how you take care of the problem of an increasing dimension. And so I hope that you've learned something from our presentation today. And if you have any questions, you can leave them in our comment section. And thanks for watching.